Hello students. Good afternoon everyone. I hope you are getting my voice clearly. Just let us wait for a minute, let others to join. Students are getting my voice. Someone drop me a message. Are you getting my voice? Right. Okay. Yes, let us start with. So one small concept is left over, and we'll finish it briefly, and we'll let us try to work out some numericals. And if possible, we'll try to have one more session in the evening to work out few more numericals. Okay, but that if there is a possibility, if it is required, I will let you know. But for time being, we'll let us continue. Let us go ahead with this session, and now we'll try to work out some questions based on the important methods. First, yeah. The small concept which is left over is just a minute, students. Let me take the earphones. I hope the voice is not that clear. Good afternoon. Good afternoon. Yes, yes. I'm checking the voice from my side as well. I hope the volume is little less. So let me. Right. Okay, guys. So the small concept which is left over is DC circuits, and in this DC circuits also specifically we need, because we are dealing with EMI, electromagnetic induction, especially inductors, inductor based questions. Little you need to just have a look at. But in NEET point of view, as already I have mentioned, it till now, if you observe the previous year's questions, till now no question is asked based on this concept. Okay, in all the previous NEET exams. But if at all you come across in this future years, you should be able to have an idea about how to deal with them, right? For that purpose, I would like to give you brief idea of this DC circuits. DC circuits. So let us consider. You can note down the subheading: DC circuits. DC circuits. Here we come across two kinds of DC circuits: LR circuits and CR circuits. First we consider LR circuits. First we consider LR circuits. LR circuits, and specifically here LR circuits means inductive and resistive circuits, or inductor resistor circuits. So let us consider there is an inductor and a resistor, inductor of inductance L, resistor of resistance L, and these two are connected in such a way that you can also say this is a resistor or internal resistance of the inductor also sometimes you can consider. Okay, so if these are connected in such a way that if these two are connected to a power supply or a battery of EMF E, and if you connect this to a key, a three-way key, you consider here, if you consider a three-way plug key, if you can take this as terminal A, B, C, and this part is connected here to complete the circuit. So why it is required, you may understand in the due course. So if you connect this C to A with the help of a tapping arrangement, this part of the circuit will be closed and the current will be flowing through this and flowing through this and flowing through this, and circuit will complete in this way. When this is moved from here to here, it will be disconnected from the battery, and when it is connected to battery, energy will be drawn from this, or current will be drawn from this. Current will be drawn from the battery. Whereas when this is connected to this, no current will be drawn from the battery. Already whatever the here during the what do you call passage of current, it may store some energy in the inductor, that will discharge us, that will pass us through this other part of the circuit. What that we call it as a decay circuit. When it is connected, this switch C is connected to A, in this case a current is said to be growing slowly in this. We call it as you can call this current is a growth current. When it is connected to here, the current flowing in the circuit will be called as a decay current, right? How they will happen briefly we'll see, not in detail. So in this case, if it is connected to this and when current starts flowing here, EMF will induce across this and across this also. So EMF, as because these two are appear to be in series, the EMF across this plus EMF across this will be equal to EMF of the cell, and EMF across this will be taken as induced EMF E, and across the resistor will be taken as IR. If current I is passing here, then it will be taken as IR. But when current is passing from in this direction, means you have to take this as a, usually current will considered to be flowing from higher potential to lower potential. This will be taken as plus and minus, so potential difference will be taken as here negative potential. This also here, when current is flowing here, the coils through these coils, due to its self-induction, EMF will induces, that is, this is the you can call it as the induced EMF. Actually speaking, EMF induces in this when current flows. That induced EMF for this plus this will be equivalent to this. So by by applying what you call Kirchhoff's laws, we can say EMF across the EMF of the battery. Algebraic sum of the potentials in a closed loop equal to 0 you can take. So E, when you are going from in this direction, right, this will be positive, but EMF of this will be
negative EM, so negative value you have to take, because the flux will be linking in such a way that you get phi equal to minus, what do you call, E equal to minus d phi by dt. So it will be minus d phi by dt will be taken as minus L into di by dt. So minus L self inductance into I into di by dt. Di by dt, the current will be varying in the inductor. So minus IR equal to 0, minus IR equal to 0. This can be taken as E minus L into di by dt equal to IR. Here this I will be the current in the circuit. This will be is not a steady current, it is a variable current. You can say that current will be growing slowly in the inductor, that growth current. Or you can say that the current, when it is passing, the inductor opposes the growth of current. Actually it will be increasing slowly, and EMF induces, and hence induced current will be produced in the coil. This will opposes the cause which is producing it. That cause is nothing but this current. This is actually current drawn from this, and due to this induced current will produce in that induced current will opposes this. Okay, so inductor will opposes the growth of the current in this. Inductor opposes the growth of current in this, right? So this current is appeared to be on solving this, we will come across a relation for I. That solving part we are not dealing step by step. On solving we get the current will be varying. The variable current is given by I is equal to maximum current I naught E into 1 minus e power minus tau by lambda. T, some books will give it T or tau or whatever it is, by lambda. This is called time period. What time period is? This called, in case of LR circuits, it is called as inductive time period. Inductive time period. Here we can say, you can take this as equation 1, where tau is called time constant. Actually speaking, not time period, time constant, inductive time constant. It is a inductive. You can also call it as a tau L. So it is equal to tau or tau L, inductive time constant. Inductive time constant. This time constant will be defined in a different way. Now, what is the different way? Is this is defined as tau L will be taken as a lambda. If it is lambda, then I will become, if this is lambda, then e power minus 1 will get 1 by e power 1 by e will get, usually by substituting the value of e and simplifying this, we will get I will be equal to 0.63 times I naught maximum value, or you can also call it as 63% of maximum value you get when tau equal to lambda, where this lambda is called as of course will be called as can also called as decay constant, or here growth constant, and it can also be given as for LR circuits L by R. So inductive time constant is given as L by R. When this is L by R, then the current in this will become 63% of the maximum current. Okay, and you can also say current, this current, of course, to reach the maximum current it takes so much of time. So here, if you want to draw a curve between I and T, that is how it will vary with T. You will get a graph. We'll call this one like this. We'll get growth current curve or graph. If you consider time x-axis time, y-axis current, time t equal to 0, of course time t equal to 0 current will be 0, right? In the expression also, if you consider here, then time t equal to 0, e power minus 0 is 1, so 1 minus 1 is 0, so we'll get the current will be 0 in this expression. And as current increases exponentially, it will increases exponentially, the current will increase exponentially and become steady. So this maximum current, steady current, will be taken as I naught. So here, when this T is equal to lambda, the corresponding, when T is equal to lambda, that is L by R, the corresponding current will be equal to 0.63 times I naught, or 63% of I naught. So this is what you can understand from this graphical variation of I also, right? Whereas during, if here simply you can say what is the maximum value of current, means if internal resistance is 0, you can see the maximum value of current can be taken as I naught, where I naught can be taken as simply I naught is equal to total EMF of the cell by resistance, external resistance. This is actually I naught. So this I, with the time it will be changing, and at this time it will be 63% of this maximum value, this maximum value. And when it is connected to A, the current starts growing. That can be understood with the help of this one. So it is given by this relation and graphically also this. Whereas if this key, a tap key, is connected to this after some time, after charging to the maximum value, or after inducing, or whatever it is, after charging some energy in this inductor, then what happens is whatever the induced charge is there in this induced EMF is there, that will decay, and hence the decay current will flow. Immediately it will not become zero. It will try to decay from the maximum value to slowly to zero. And how it will happen, we'll see with the help of a graphical relation here. So to understand this, we have to take one mathematical relation as well. Let us take this as a decay current. Decay current. The decay current, if you observe here, that means from a maximum value it will decay. If you observe the previous expression, it will increase from 0 to maximum value. For here it will decay from maximum value, but exponentially. That is given by, decay current is given by, at any time, at any instant of time t, is I is equal to I naught. That means if you, in the above expression itself, at time t equal to 0, if you take, it becomes this, right? So that's time t equal to 0, it becomes 0. So whereas the maximum current means after infinite time, e power in minus infinity is 0, it will become maximum. In this, the steady current, it takes infinite time, relatively infinite time. So at infinity, if it is I naught, from that value it is supposed to decrease. That is given by I equal to I naught into e power minus t or tau by lambda. Again, lambda is same, time constant, right? Decay constant. This is inductive time constant. This is decay constant actually. So don't actually here compare. I mean, confuse this relation lambda with the lambda comes in what you call in one of the chapters. Atoms and nuclei also will come across there. This kind of relation, right? The decay ratios. Then disintegration constant, we call lambda there as a disintegration constant. Similar kind of relation will come across there. So, so don't confuse about this, but the variation represents a similar kind of variation only. So here at time t equal to 0, e power 0 is 1. So we'll say at tau, at t is equal to 0, e power 0 is equal to 1. So we'll get I is equal to I naught. Time t equal to 0, it will have maximum value. So when time increases, then it decreases because of this power, negative power. So how to express this is I, this is t. At time t equal to 0, it will be having maximum value I naught. From here onwards, from here it will, the value will decreases exponentially, and it takes infinite time for this to becomes to 0. And here also you have to understand that when lambda tau equal to lambda, that is inductive after inductive time constant, r that is equal to L by R. Here when tau is equal to L by R, L by R or lambda, we'll get 1 by e power minus 1 is equal to, actually is lambda. So if this is lambda cancel, e power minus 1 will get, so that is 1 by e, it becomes I naught by e, it will become, then I will become 0.37 times I naught, or 37% of I naught it will become. The current after this time, it will become what you call, you can say when t is equal to, when tau is equal to lambda, the corresponding current will become I is equal to 0.37 times the maximum value. Okay, so this is during the decay. So so that means the rate of decay of current for small values of I, or for small values of I, it will be so quickly it will decrease. For larger okay, or you can say the for small values of L, you can consider as a tau is equal to L by R. For larger values, it will take slowly, the decay will take slowly. In CR circuits, we will deal with charge, growth of charge and decay of charge, instead of growth and decay of current. That is the difference between LR circuits and CR circuits. That's it. Now let us see few questions based on, but only the difference is, apart from that, the other difference is the time constant in CR circuits is tau is equal to CR, whereas in case of LR circuits, time constant is L by R. Time constant here is L by R, whereas in case of inductive, this is the time constant of inductive circuit. Time constant of capacitive circuits will be CR. That is the difference you have to just keep in mind. Now let us see, based on these few simple numericals, along with this few important numericals as well. Let us see question number from like randomly few questions in this. So especially first we'll see few questions from LRCR circuits. In level 1 exercise 2, level 1 exercise 2, let us do few questions. Level 1 exercise 2, page number 109, question number 21, question number 21, page number 109. So what is given here and what you are asked to find and how to do it? It is given that a coil is connected to a battery. A coil is connected to a battery of 12 volts EMF, 12 volts, and negligible internal resistance, means there is no resistance. The coil is not having any resistance, negligible resistance. The current in the solenoid grows to 63% of its final steady state value in 0.3 seconds. The time taken to increase for this value 0.63% is called as a time constant, right? So that is time constant. Tau is equal to L by R is equal to 0.3 seconds. In this time it has increased to 0.63%. That is the meaning of it. So here, if we say, let us say the inductance of this inductor is L, and if the steady state current is 0.6 ampere, the inductance of the solenoid is what? If the steady state current I0 is equal to 0.6 ampere, then what is inductance of the solenoid? L is equal to what is the question? What is the inductance of the solenoid? How to get it? We know from the time constant, L is given. Can you make use of this concept of time constant? So if you take this as a closure circuit, usually it will be a resistor which will be here, but there is no resistor because its internal resistance is considered to be 0. Now here, as we know, as tau is equal to L by R. R value is not mentioned, so we cannot take it as the external resistor value. Internal resistor value is 0. But external resistor is not given, then you have to take it as in terms of potential and current. So from Ohm's law, V is equal to IR. R is equal to V by I. So from this you can write it as L I by V. You can take R is equal to L V I V by I. So then you will get tau is equal to L I by V. So here, if the maximum current I0 is 0.63, then here what is mentioned? Yeah, if the final steady state current is 0.63 ampere, the inductance of the solenoid is what? Inductance is how much? So from this you can say L is equal to tau into V by I. Here you can take it as this value, you can take it as I0. Tau value is given, and V value is also given here. What is V? This is, you can take it as V or E. It is given as E or V is equal to 12 volts. Then maximum value of current, if you take this as the corresponding maximum value of current, you can it is given as 0.6 ampere. For this, what is the corresponding inductance value is you are asked to find. As time constant is 0.3 seconds into V is 12 by I0 is 0.6, then so we'll get approximately so exactly is 0.3 by 0.6 gives 2, so equal to 6. What is the SI unit of inductance? Henry. So we'll get 6 Henry. So therefore L is equal to 6 Henry you will get. Like this you have to work out this kind of questions. Whereas if you observe the other questions also, the similar kind of procedure you can make use of. Let us see question number 23. What is given and what you are asked to find here? what is given and what you are asked to find here. You can understand. An ideal coil of 10 Henry is connected in series with a resistance of 5 ohm and a battery of 5 volts. 2 seconds after the connection is made, the current flowing in the circuit is, after 2 seconds, what is the current flowing in the circuit is the question. After 2 seconds, what is instantaneous current is how much is the question. So question number 23, let us see. Question number 23. It is given that an ideal coil of 10 Henry is connected, means that is 10 Henry is inductance. L is equal to 10 Henry is connected in series with a resistor of resistance 5 ohm and a battery of potential or EMF E equal to 5 volts. 2 seconds after, means after t is equal to 2 seconds, the connection is made. 2 seconds after the connection is made, the current flowing in, and the current is what is I? You don't know I naught. So but by using this, you can if you say this is L R, they are connected in series to a battery, then you can find out what is this L and R and E. You can find out I naught. Maximum value of I can be taken as, from this as I naught is equal to E by R. E by E from Ohm's law equal to IR. So it is I naught equal to E by R. I naught is equal to E by R. So what is this value? So E is how much? E is 5. R is also 5. So 5 by 5 is equal to 1 ampere. 1 ampere is I naught value. 1 ampere is I naught value. So by taking this here, we are supposed to find out I, instantaneous current. After t seconds, what is the current in the circuit you are asked to find? So the current which is varying with time is given by, we know that I is equal to I naught E into 1 minus E power minus tau by lambda, minus tau by lambda, right? So or you can say minus t by lambda. So the time, if this time is equal to lambda, then we call it a decay inductive time constant. Inductive time constant, it is equal to 63%. That is a different thing. But here after 2 seconds, what is this? The lambda is time constant, which is equal to L by R. The lambda is time constant, right? So lambda is also called as time constant, which is equal to L by R, which is equal to L is how much? 10, R is 5, which is equal to 2, which is equal to 2. So the question is, after 2 seconds, if you want to know what is the current, I is equal to I naught is already have discussed, I have calculated here 1 into 1 minus E power minus, after how much time? 2 seconds. What is time constant, corresponding time constant here? 2. Then it becomes 2 to cancel, E power minus 1 it becomes, it is equal to 1 into, so that means 1 only, 1 minus E power minus 1 it becomes, so E power minus 1 is 1 by E. So that will be the value of current after 2 seconds. So here, if the values and the options are given in terms of numerical value, you have to substitute the value of E and you have to find out the final value. Otherwise, depending on the options, you have to keep as it is. So according to the options, the current after 2 seconds is options are given as 1 minus E power minus 1, 1 minus E power minus 1, like that. So you can take it as I is equal to 1 minus E power minus 1. E power minus 1, that is the current after 2 seconds. So you can keep this as the answer. That's it. This is how we have to deal with this kind of questions, right? This is briefly about what you call it, DC circuits. Usually LR CR circuits. LR circuits are important, as I told you, for our case. But in CR circuits, charge variation you have to come across. Instead of current, you have to use charge variations. That means just I will give you what you call brief relations for LR circuits. CKT means circuits. I is equal to I naught into 1 minus E power minus T by lambda, where lambda can be taken as time constant, which is equal to tau, which is equal to L by R. Here lambda can be taken as tau. Of course, when it is equal to tau, it is a different thing, but when time constant, in this case the inductive time constant is equal to L by R. Got it? Where current will changes during growth, during decay, just I naught into E power minus T by R. Whereas in case of CR circuits, we come across, instead of current, charge Q is equal to Q naught, maximum charge into 1 minus E power minus T by lambda only will come across. But here that a time constant will be taken as capacitor time constant, it is equal to CR. Instead of L by R, here we will get C by R. When lambda is equal to C, then here the same conditions will apply. The charge becomes 63% of the maximum charge, etc. Those conditions will be same as it is, just like this. Okay, these are briefly a few points related to this. Now let us see few more questions. Some what do you call randomly few questions based on EMF, motion EMF, etc. Okay, so let us see in this in this itself, level 1 exercise 2 itself, level 1 exercise 2, level 1 exercise 2, question page number 108, question number 12, question number 12, page number 108. So what is given here and what you are asked to find? Let us see. It is given that a thin flexible wire of length L is connected at two adjacent fixed points and carries a current I in the clockwise direction as shown in figure. As shown in figure, it is flowing in a clockwise direction. When the system is put in a uniform magnetic field of field strength B going into the plane of the paper, the wire takes the shape of a circle as shown in figure. Then the tension in the wire is what? Then the tension in the wire is what? So how to calculate this? Let us see. Question number 12. Yes, according to this, there is a wire, some what you call a loose wire or not stiff wire is there. In this, a current I is flowing in clockwise direction. A current I is flowing in clockwise direction. Now this wire, if you keep in a uniform magnetic field, if you keep this in uniform magnetic field, this kind of uniform magnetic field, it is observed that it takes the shape of a circular coil, circular loop. It takes the shape of a circle. So it becomes, in this uniform field, it becomes a uniform circular shape. It takes the uniform circular shape. I have to take little properly. It takes the uniform circular shape. Right. Why? Because whenever a current is flowing in a wire, and that wire if you keep in magnetic field, a force will act on the current carrying wire or coil in magnetic field. That force on current carrying coil is given by FB. Magnetic force is equal to current in the coil into length of the portion of the coil into the strength of the external field where you kept this. So ILB is the magnetic force. But here, because everywhere magnetic force acts in such a way that it will become stiff, and that means a tension will develop in the wire everywhere. The tension is provided by this magnetic force, and hence it will take the shape of a circle. So how can you understand that is? If you let us consider a part of the circular loop, you can call it as arc of circular loop of radius r, and this is this part, arc of circular loop. Let us say its length is L or dl, any symbol you can use, length L, and if it is subtending some angle, small angle theta at the center, this arc at the center, then we can say according to the expression force on current carrying loop in uniform magnetic field, if you use the right hand or right hand rule, I into L cross B in vector form, if you observe, FB is equal to I into L cross B. So L will be taken as in the direction of current. If the current is flowing in a clockwise direction, magnetic field is into the plane, so L cross B will be upwards. So magnetic force on this will be in upward direction. Okay, but the resultant one, right? If it is moving in anti-clockwise direction, then it will be downward direction. It will be in downward direction. But actually, if you consider this force is giving you here the tension, at every portion of tension will act on the wire. Here by symmetry, this is total angle subtending by the arc at the center is theta. Then you can take this as theta by 2. This also will be theta by 2 by symmetry. You have to follow this carefully. And now, if you consider there is a tension T is acting here by symmetry, the angle made by this with the horizontal, this is theta by 2. So this also will be by symmetry. This also will be theta by 2. So similarly, this is tension T, this is theta by 2, then by symmetry this also will be theta by 2. If you resolve this t into rectangular components, you will get t cos theta by 2, and perpendicular component will be t sin theta by 2. T sin theta by 2. Here also t cos theta by 2, and here in perpendicular component will be t sin theta by 2. T cos theta by 2 will cancel out here. T sin theta by 2 will add up to provide the magnetic force required for the ring. So you can see that this magnetic force is provided by the tension here, provided by the tension, or you can say the net tension acting on this. Net tension is acting on this is nothing but this is I into L. Here length of this arc in terms of this, if this is a radius r, then it can be taken as L is equal to r theta. L b into r theta will be equal to, when it is making a subtending an angle theta at this center on that arc, then it is equal to net torque will be this component of torque plus this component of torque, t sin theta by 2 plus t sin theta by 2 becomes 2t sin theta by 2. 2t sin theta by 2. So for smaller angles, here we have to say for smaller angles, sin theta can be approximately taken as theta. So sin theta by 2 approximately will be taken as theta by 2. So this can be expressed as IBR into theta is equal to 2t into sin theta by 2 can be taken as theta by 2. So here 2 cancel, here t into theta is equal to IBR into what? Theta. So it becomes theta gets cancelled. So the tension developed in this wire will become T is equal to IBR. This is the actually the tension developed in the wire. The tension in the wire is this. But if you see the options, IBL by pi, IBL by 2 pi, IBL by 4 pi kind of expressions are there. IBL form the given, but not in terms of R. But if you take IBL, you cannot say even simply you can take cannot take IBL here. Why? Because this is length of the arc. So that length of the arc you can take this as for this an entire circle. That length of the tape can be taken as actually radius as circumference. Total length is nothing but circumference, as total length L is equal to 2 pi r. You can, from this you can say r is equal to L by 2 pi you can take. So in terms of L, if you replace here, then you'll get tension developed in the string is circular, in the circular shape is IBL by 2 pi. This will be the tension developed in the string. This will be the tension developed in the string. Okay, right. Yeah, and one more question has asked by one student yesterday. Just I thought to discuss that as well. From level 1, exercise 1, I think. Yes, let me check that question. Right. So right now immediately I'm not able to get that question. Okay, then I will discuss that later on. Now just I would like to just discuss briefly one of the previous year's question, that is given in level 2 exercise 2. You see here page number 116. Page number 116. So randomly few questions just we are looking at. Question number 15. Question number 15. So one of sorry, not 15. Actually, one of our student has asked this question. Question number 4. Question number 4. Right. So what is given here and what you are asked to find? What is given here and what you are asked to find? Let us see here. It is given that two identical conducting rings A and B of radius R, capital R, are rolling over a horizontal conducting plane with the same speed v but in opposite directions. A constant magnetic field B is present pointing into the plane of the paper. Then the potential difference between the highest points of the two rings is. So let us copy the diagram, pictorial representation of this. Then you can understand it more clearly here. So what is given here is two identical conducting rings A and B are given, and they are lying on a conducting plane. There is a plane. On this plane, two rings at this. I am not drawing this properly. You can take a regular shape one. Yep. Yeah. There is this one ring, and there is another ring also. Not this one. Yep. You see. Another ring, similar one. Yep. So there are two rings. You can take the shapes properly. So these two rings, A and B, marked this as A and B. This is A, this is B, and two identical. Identical means same radius and same made of same material. Everything will be same. That is the meaning of identical. These are moving with two identical rings A and B of radius. Both are having same radius, R and R. Having same radius, are rolling over horizontal conducting plane. This is a plane which is conducting plane. It's a metal conducting plane with same speed v but on opposite directions. This is moving in this direction. This is moving in forward direction, but with same speed. They are moving with the same speed but in opposite directions. And a constant magnetic field is present pointing into the plane. Here actually these are kept in uniform field, which is directing into the plane. Uniform magnetic field acting into the plane. B is acting into the plane of the paper. Right. In this field, when a constant magnetic field B is presenting pointing into the plane of the paper, then the potential difference between the highest points of the two rings, when they are moving, what is the potential difference here and here? So that what is the difference between them? Let us say this is the first one, or A. What is potential here? And VA, what is the potential here? VB. That what is the difference between these potentials is the question. What is the difference between the potentials at these highest points? Let us mark this with differently also. Let us take this as a point. Actually, you can take this as point 1, 2, 3, 4. You can give some names to them. You can give some names. 3, 4, 1 and 2. So you have to deal this as like a coil moving in one single coil. When a single coil is moving in a uniform field, you have to consider to find the potential difference between this opposite diametrically opposite points here like this, and it is when it is in contact with this. Due to here motion, the EMF induced at these 2 points will be given as induced EMF will be taken as B V into L effective. L effective for this these 2 points is nothing but 2R. If this is radius is radius is R and R will be 2R, so it will become 2VRB, 2VRB or 2BRB. And here also for this also potential will be same. V into L effective. V is same. B is same. B is also same. L effective will be 2R, so this also will be 2VR, but the direction if you observe, potential difference between these 2 points is potentially here, if you use the right hand what you call palm rule, if you stretch the fingers, let me show you here with the help of uh, yep, visibly, right? So if you consider what do you call right hand Fleming's right hand rule or right hand palm rule, according to Fleming's right hand palm rule, according to Fleming's right hand palm rule. If you stretch the fingers of right hand into the plane in the direction of magnetic field, and thumb if you stretch in the direction of velocity, then the palm direction will give you the positive potential one. So in this case, if you observe, if you stretch the thumb in the direction of velocity on what is that, on coil B, if you observe on coil B, if you stretch the thumb in the direction of velocity and fingers in the direction of field, that is into the plane of this, then you can see the palm is upwards, means upward point will be at higher potential. So this will be the higher potential point. This will be the lower potential point. So the induced EMF will be in this direction, and hence induced current will be in this direction. So as this is a conducting plane, this is placed at a conducting plane, this will act like a wire, and it again here for this again if you use the same relation here, if you observe like this by using the same right hand what you call right hand palm rule. So according to this right hand palm rule, if you stretch the fingers into the direction of magnetic field, and if you stretch the thumb in the direction of velocity, the direction of palm gives the higher potential direction. This will be higher and this will be lower potential. So this potential difference here is nothing but higher minus lower, that is V2 minus V1. That means for this is a higher potential. So potential at this point is nothing but these two are common potential. So you can say the difference between them will be zero, right? But here these are at a different potential. This is at higher potential, this is at lower potential. So you can take this as a V at 2. The induced EMF at the second point is nothing but 2 VBR, and induced EMF at the fourth point, at point 4, is nothing but minus. Actually, this is also BVL effective, but because of the direction, you can take it as minus 2 VRB or 2BR, whatever the options they have given as 2 BVR form they have given. In the same form, you can write 2 BVR is equal to minus 2 BVR is this. Now the point is, the potential difference between the highest points of the two is potential difference between these 2 points, that is E4 minus E2 or E2 minus E4. E2 minus E4 if you take, so delta E is equal to, what is that? E2 minus E4 is equal to, E2 is 2 BVR minus E4 is minus 2 BVR, minus of minus becomes plus 2 BVR, it becomes 4 BVR is the potential difference. That will be the effective potential difference between these 2 points. So the option 3 will be the correct one for this case. So this is how you have to deal with this kind of questions. Okay. So this is briefly about what you call EMI and the important points in this particular chapter. And you guys try to work out few more examples. Actually, one of the student has asked a few more one more question. Actually, just I'm not getting it immediately. So I would like to have one more session for discussing a few more questions, guys. So you try to send me the questions if you have any doubts. So those questions also just we will discuss in one more session if possible. Today evening I will try to have, otherwise tomorrow just we'll try to take one more session and we'll discuss the remaining questions. Okay. So with this, actual part of the weekend portion part is completed with important methods and the numericals. So you guys have to work out more and more numericals. Just I want to cross check whether you know each and every question, and especially in level 1 all questions. So question wise I want to cross check. So I would like to take one more session. Only numericals we'll discuss. Only numericals. Let us check whether you know which one you are having a confusion or a doubt like that. By with kind of discussion, we'll go ahead with each and every numerical wise. So level 1, both exercises you have to finish all the questions. Then you will come to level 2. We'll try to cross check all the questions. Okay. So you guys check it once, and if you have any doubts, just send me a message so that we will first focus on those, then the remaining questions. So okay, then I am winding the session now. I say take care everyone. Bye bye.